Hey everybody, by the end of this video I'm going to show you how to use buffer calculations to, let me make sure that I'm back on the right thing, buffer calculations to understand how a titration works, and then hopefully be able to find the pH at different points through a titration. Now, a titration, just so everybody knows, is a way of adding a strong acid or strong base to a weak acid or weak base. Okay, and so by doing that, that changes the pH. Now, keep in mind that a buffer is something that resists change to pH. The best example that I have of something that resists change to pH is blood. If blood changes pH, then you are not going to be able to function properly, and that's important. So as you add things to your body, as your blood needs to stay at a certain pH. And so we can do something called a titration that monitors the pH over time, and as the pH changes, or as we know that the concentration has changed. So we do titrations in the lab to determine the concentration of either the weak acid or weak base, the buffer solution, at certain points. One of the most important points is this, called the equivalence point. And so this is probably this section about titrations and adding weak acid, or adding strong acids and bases to weak acids and or bases, is probably like the longest part, or the most difficult part to understand. It's not horrible, but you have to make sure that we take it kind of slowly. Okay, so let's move forward here, and let's talk about what happens when a strong acid or a strong base is added to a buffer. Okay, now in this case, not in this case, in all cases, there are two parts to this sort of problem, what I call a titration problem. You'll see that there's the first part where you have the stoichiometry, or the stoichiometric calculation. Let me take this and move this somewhere here. Okay, I can move it here. Okay, and then the stoichiometry is when the strong component reacts with the buffer. Okay, that's here, and that's what this is. Okay, we call that the neutralization step. And then the second step, or the second part, is determining the pH using the Ka or the Kb. Okay, so, and this is the equilibrium step. Okay, so there's the stoichiometry step first, followed by the equilibrium step. Okay, so I think that it's important to work through one of these problems so that you can see kind of what it looks like. Okay, so this is another visualization of what happens when you do a titration here. Okay, so here's your buffer solution right here. Okay, and then they add 0.02 moles of hydroxide. That raises the pH. Okay, and it raises the pH by 0.06 units. And then here we add, if we take that same buffer, instead of adding the base, we add the acid. Notice that this lowers the pH by 0.06 units. Okay, by adding the strong component, notice the pH doesn't change, but we change it. Okay, it doesn't change much, I guess is what I should say. And so when it doesn't change much, but it still changes, that's how we know we have a buffer solution. Okay, you can use the Henderson-Hasselbalch equation if you want, but let's talk about this problem right here. So we have acetic acid. Okay, it's a buffer solution of acetic acid and sodium acetate. Okay, how do we know what that is? How do we know that that is a buffer? Because it's the weak acid and it's the conjugate of that weak acid mixed together. Okay, and we have that the pH of the buffer is 4.74. And then it says calculate the pH of the solution after 0.02 moles of sodium hydroxide is added. Now, when we do these sorts of problems, again, we have to do them in 2 steps. If this was just a buffer problem, okay, if it was just a buffer problem, we would only have to worry about the equilibrium step, okay? But the context clue that tells you that we have to do the 2-step titration problem or adding something problem is this guy right here. Whenever you see that something is added to a solution, weak acid, weak base, typically you have to do it in 2 steps. Okay, so let's see what happens here when we do this problem. So I've put all that information from the PowerPoint right here into this document. That way we can, or this notebook, so that way we can do the required steps. So before we get started, one of my big things that I like students to be able to do is visualize what's going on. Okay, so realize, in my effort to try to get you to visualize this, realize what you have here is a beaker or a flask, and inside the flask you have a solution of this thing, and this thing in blue is a buffer. Okay, now what you're experimenting with is you're going to take 0.02 moles of sodium hydroxide and you're going to add that, and so this is kind of the titration part. Okay, may not happen as a titration, but that's kind of how I'm going to phrase it. Okay, I guess you could just dump it in there if you wanted to. Okay, now again, because it's being added, because we have this green thing, this stuff in green that I've donated with, or denoted with green, because you have the green thing and that's being added to the buffer, we need to do this as a 2-step problem. If we were given only the stuff in blue to figure out the pH, this is just a 1-step weak acid equilibrium problem. It's not until you add something that it becomes a 2-step problem. But okay, enough about all of that. You want me to get started. Okay, so something new but not new. Okay, before we do the equilibrium, we have to do the stoichiometry steps. So what I'm going to do is I'm going to write stoich, because I don't want to write stoichiometry out. So this is going to be the stoich step. And whenever we do the stoichiometry step, just like when we do weak acid and weak base, there's specific reactions. This is going to be a specific reaction. So anytime we do this, okay, what we need to do, we have the base. Bases will always react with acids. So of these 2 things, this or this, which one is the acid? Okay, so we know that we have hydroxide, but now we need the acid. Well, this is the Bronsted-Lowry acid. This is its conjugate base. So the thing that it must react with is this, HC2H3O2. Okay, and then that happens to be a 1-sided reaction to get H2O, because this donates to there, plus C2H3O2. Okay, so now when we do the stoichiometry part of this, because we've added something, when we do the stoichiometry part of this, okay, we do it in units of moles. It makes it way easier to calculate it in units of moles. In this case, the problem that we were given, we have moles for every 1 liter, so it's a little easier, but make sure you do the stoichiometry step in moles. Now, best part about this, You can still use an ICE chart because what we want to know is how much of everything is left. Okay, and so hopefully this will kind of also explain the chemistry of why a buffer change doesn't allow the pH to change. So how many moles of hydroxide do we have? Well, we have 0.02. How many moles of this do we have? 0.3. Water doesn't matter. And then how many moles of the acetate ion do we have? Well, back up here we have 0.3 again. And again, sig figs, I'll worry about at the end. All our values are going to have 3 significant figures. Okay, so now stoichiometry, we have to go through, we have to figure out what the limiting reactant is. Okay, well, the limiting reactant is the thing that is present in the least amount. And typically, when we're doing stoichiometry for acids and bases, hey, look, it's pretty straightforward. And that is what makes a buffer work. This, the hydroxide, is the limiting reactant. So because it's the limiting reactant, we are going to lose all of it. Okay? And so how much strong base is left after the reaction is over? None. That's how a buffer works. A buffer works by eating up or chewing up, or more technically reacting away, all the strong acid or strong base in this case component, and then you're left with weak components. So we finished the stoichiometry. This is a 1-to-1 ratio, so we are going to lose 0.02. And now over here, again, this is a 1-to-1 ratio, so we're going to gain 0.02. And so what is this? 0.28 moles, and this is 0.32 moles. Okay, so now once we have that, now we can do our equilibrium step, because now we know how much stuff we have that is going to reach equilibrium. And again, I can't emphasize the chemistry enough here, is that the buffer works because now we don't have any hydroxide left. Hydroxide is the strong base. If there's none left, now we're stuck doing equilibrium to figure out what the pH is based on how much of the weak acid and its conjugate there are. Okay, so now because we're doing the equilibrium step, okay, the equilibrium step with an acid is going to be the same reaction as we've always done. Okay, the weak acid, HC2H3O2, that's acetic acid, plus water. The acid plus water is in equilibrium with the hydronium ion plus the acetate ion, C2H3O2 minus. Okay, well now, because this is going to reach equilibrium, how much of each of these things do we have? Well, at the beginning, we're going to have as much as the stoichiometry step told us. So how much of this do we have? We have 0.28 moles. Okay, how much of this do we have? We have 0.32 moles. How much of this do we have? We don't have any, and water doesn't matter. Okay, so now if we want to find the pH, we're looking for this box right here in your ICE chart. And now we can go back and fill it in and do just a regular, I say regular, but kind of it's just a standard weak acid equilibrium. So we're going to shift to this side, to the product side. So we're going to go minus x plus x plus x, okay, 0.28 minus x, this is going to be x, this is going to be 0.32 plus x. Okay, now the Ka of this, 1.8 times 10 to the minus 5. I don't know if that was given to you, but it would have had to have been given to you, because in order to calculate the pH, you need either the Ka, okay, and then this is products, x over 0.32 minus x, all over 0.28 minus x. Now, now at this point, we've done all the chemistry, and now we can do the math, okay? So, get rid of the good titrations. It was a lot there that my calculator was hanging in. Okay, but now, so it's 0.08, or sorry, 1.8 times 10 to the negative 5. Okay, and just for clarity, these x's we're going to get rid of. Okay, this is plus, right? And then we got rid of that. Okay, so it's going to be that times 0.28. Okay, and then divided by 0.32. When we do that, we get x equal to 1.57 or 1.58 times 10 to the minus 5. Okay, and so that changed only very slightly the value of x. That's because this ratio here is still around or close to 1 to 1. Okay, when we think about buffers, this ratio is the important ratio, the ratio of the acid to the conjugate to the acid. Okay, and so because that's still close to 1 to 1, this is still close to what we get. Now, that equals the concentration of the hydronium ion, but that is not yet the answer because now we have to do the pH. So we're going to do negative log of that, and we get 4.80 equals the pH. Okay, and so that's how we do that problem. We do it in steps. Okay, so hopefully you get how to work through this problem. I'm going to post some other sample problems on this sort of thing, and have a great day.